While discussing shortest job first, we assumed we know the length of the next CPU burst. But how can we predict the length of the next CPU burst? That's still an open problem. What we can do is we can look at what has already happened and we can make some estimations for the near future. So assume that we have already observed the nth CPU burst, okay? And we're trying to predict what will happen for the n plus first CPU burst. So if what I have already observed for the nth CPU burst is represented by T sub n, I can predict what the length of the next CPU burst in the n plus first CPU burst will be as tau sub n plus 1. Here we're going to use a weighing parameter represented by alpha, which is between 0 or 1. 0 and 1, typically what we use for weights. So we define the predicted value for the n plus first CPU burst as alpha times what we have already observed for the previous CPU burst plus 1 minus alpha times what my expectation or estimation for that CPU burst was. So once again, it is with weight of alpha, the real observation, plus with weight 1 minus alpha times my previous estimation. Now, this is a recursive definition actually, because tau n plus 1 depends on tau n, and tau n depends on tau n minus 1, which depends on tau n minus 2. It goes this way. But note that these all also depend on the previous observations. That's the important thing. In general, we take alpha to be 1/2, but of course it could differ. Now, this is actually how you can, in reality, implement shortest job first. But note that this is based on not reality, but our predictions. If our predictions hold, then it will be real shortest job first. If our predictions do not hold, it will be something close to shortest job first. How close? Well, it depends on how close your predictions were to reality. Now, in the case of shortest job first, remember, we have a process, we have the list of available processes at that moment, okay? And we make our decision based on the next CPU burst and say we're going to execute these processes in this given order, whatever it is, like 4, 2, 3, 1, whatever order. What if not all of the processes were available at the very beginning, but some of them come a little bit late? Like while executing some of the processes, another one arrives. Another one arrives. Okay? Now, you have already made some decision, and what if the new one that arrives is shorter? Our idea was to do the shortest ones first. That's what SJF says, shortest job first. But the shortest one was not available at the time I made my decision, so I didn't know about that one. I started with a process, and then shorter process arrives. In regular shortest job first, that process will have to wait until the current process ends, and at that moment, while making the decision for the next job to go to the CPU, now I will consider that new process, which is quite short. That would be a non-preemptive implementation for shortest job first, because although the new process is shorter than what I already have in hand, since I have started executing this process, I don't do a context switch. If I look at, if I decide to go with a preemptive implementation, I should not be looking at the length of this process, the current process in the CPU, because already I have executed some parts of it. So I should be looking at whatever remains from this process against the new process. Okay? Because maybe I've executed this process for some time and say there's only 1 millisecond remaining, and that new process that comes in is 2 milliseconds. So still this one has less remaining time, so I wouldn't do context switch in that case. But if it has more execution time left, then I decide on doing a context switch. In that case, that would be a preemptive shortest job first scheduling. This is called actually the shortest remaining time first, because this time I'm looking at the remaining times. We'll come to that. So, as I said, we're trying to make some estimations on the length of the next CPU burst. So, let's assume the black line here shows the real next CPU burst time. Okay, so in the beginning it was 6, but I didn't know while starting, I didn't know it would be 6. So I make some estimation. At the very beginning, I have no history. So how do I estimate? Well, I just make an assumption. Okay, let's say I know that on the average, the processes in my system, on the average, have a burst length of 10 milliseconds. So I estimate as 10, but the reality happens to be 6. The reality is lower than my expectation. Therefore, I start lowering my expectation. In the next burst, it happens to be even lower. So I was lowering my expectation, but reality even gets lower. So I still keep on lowering it. But then it gets higher, and now I have undershooted. So in the previous 2 slots, I had overshooted, but now I undershoot the estimation. So while calculating my estimation, now I say, okay, I should now be increasing because I have underestimated. So I start increasing my estimation. Well, it again drops and then increases so much that it takes me several rounds to catch up with the reality. Now, how fast my estimation approximates the real CPU burst lengths depends on how wildly the real CPU bursts fluctuate. If they don't fluctuate, I can estimate the next CPU burst very close to reality. If it wildly fluctuates several times, I will be either significantly underestimating or overestimating the next CPU burst. So going back to this formula, now what would be the value of alpha? Of course, the extreme cases, the boundary cases, would be when alpha is equal to 0 and when it is equal to 1. If alpha is equal to 0, then just substitute it in this formula. What does that say? It says, forget about this Tn. What was Tn? Tn is the actual observation. It's what happened in the last CPU burst. And it says, give 0 weight to that. And give all the weight to what? To my estimation for the previous one. Okay? So that also depended on my previous estimation. So actually, when alpha is equal to 0, I don't consider the recent history at all. I'm not looking at the observation, but I'm just basing my prediction for the future on my previous estimation, which was based on the previous one and the previous one. So actually, it's always the same. The first thing I estimated, like in the previous example, my estimation, the blue line would be just a straight line here at 10 because my initial estimation, somehow I picked 10, so it would remain as 10. Of course, this is not a very good approach. So picking alpha as 0 is not a very good approach. If I pick alpha to be 1, in that case, the first term here would be Tn. So the length of the actual length of the previous CPU burst, and I don't look at my previous estimation. One thing to note here is my previous estimation actually includes the term Tn minus 1, the observation before the previous one. So actually, this tau n always carries me some information from far history, and if we take alpha to be 1, we don't consider that at all. Okay, so in that case, if alpha is equal to 1, I would be looking at only the last actual observation, but not the others. As we said, typically we will take alpha to be something between 0 and 1. And if we expand that formula, we see that tau of n plus 1 is equal to tau, alpha times Tn plus 1 minus alpha times tau n minus 1, which was equal to alpha times Tn minus 1 plus 1 minus alpha times tau n minus 2. And if you substitute all these, you will end up with this formula, which is finally based on tau 0, which was my initial estimation based on nothing. I just made it up. So in the previous case, again, remember that tau 0 was 10. It's just something I made up. But other than that, that's the only estimation left. The rest is actually just the observations, but the weight is 1 minus alpha to the j for tau n minus j. Now remember that this 1 minus alpha is a value typically less than 1. Okay? Therefore, the weight of the far history is much lower compared to the weight of the near history. But this is actually a weighted historic averaging mechanism. So the shortest time first algorithm now would work as follows. Let's look at again an example. We have 4 processes again, P1 to P4, with their burst times given here in the last column. But these processes this time do not all arrive at t equals 0, but they arrive at times 0, 1, 2, and 3 respectively. So if I apply the preemptive shortest job first Gantt scheduling and draw its Gantt chart, which is actually, remember, equivalent to shortest remaining time, it would work as follows. At t equals 0, the only process I have in the system is P1. P2, P3, and P4 have not arrived yet, so I don't know about them. So, of course, there is only one option, to start with P1. Okay? So, I start with P1, and its burst length is 8. Normally, P1 is expected to come up to this point for 8 milliseconds. However, at time 1, P2 arrives. So at time 1, what's left of P1 would be 7, because I've already executed it for 1 millisecond. But P2 has a burst time of 4 milliseconds. Therefore, I would preempt P1. But remember, preempting P1 does not mean trashing all the execution I have done for P1. It has already executed for 1 millisecond. So remaining 7 milliseconds of P1 are waiting now. So P2 goes into the CPU and it starts executing. So when we come to time unit 2, at this point, as you can see, P3 arrives here. But when P3 arrives at time equals 2, its burst time is 9. And its remaining burst time is 9 because it hasn't started executing at all. Meanwhile, P2 has executed for 1 millisecond, so its remaining burst time is 3. So as of time t equals 2, what I have in the system is processes P1, P2, and P3 with remaining burst times of 7, 3, and 9. So the shortest among these is 2, so I keep on using 2. I keep process P2 in the CPU. Sorry, let me put it in a better way. So it continues. At t equals 3, P4 also arrives. So as of t equals 3, what I have in the system is P1, P2, P3, and P4. P1 still has execution time of 7 because it has only executed for 1 millisecond. But P2 now has executed for 2 milliseconds. Therefore, its remaining CPU time has now decreased to 2. P3 did not start executing at all, so it's still 9. And P4 has 5. So P2 continues. Okay. As of time unit 5, P2 will have completed. So let me just erase all these. So when time is 5, this has already completed. So it's not in the system anymore. So I'm left with, remember, this had reduced to 7. I'm left with 7, 9, and 5. The shortest one would be 5. That's why P4 goes into the CPU at t equals 5. Since no new process arrives, I don't need to consider what happens at 6, 7, 8, whatever. Because here, I've already picked the shortest one, and since it's executing, it's getting even shorter. So there is no need to consider, no need to make calculations. We will proceed until P4 completes just because no one else arrives in the system. If someone else arrives, I have to recalculate to see if I need to do context switches. But if there are no new arrivals, we wouldn't expect to do any context switches. So at t equals 10, P4 would be completed. So P4 also leaves the system now. Now I'm left with 7 and 9. P1 is the shorter one. So I resume P1. Note that P1 executes here and also here. And then when P1 completes and leaves the system, I will be left with P3, and that's only when P3 enters the system and executes. So if you look at the average waiting times, P1 has waited in the ready queue for this duration. Okay? It did not wait at all here, so I don't need to consider that. But after it started execution, it was paused and it had to wait from t equals 1 to t equals 10. Therefore, it waits for 9 milliseconds. P2 waits, how much? Does it wait for 1? No. Actually, Note that P2 arrived at 1. Therefore, and when did it enter the CPU? At 1. Therefore, its waiting time is 0, not 1. Because, once again, P2 did not arrive at 0. It arrived at 1. Similarly, for P3, it started at 17, but it arrived at 2. So it has waited for 15 milliseconds. And for the case of P4, this should have been in parentheses, sorry. For the case of P4, uh, P4 started execution at 5 and it had arrived at 6, so it's 5 minus 3, so this is 2. And if you take the average, it will be 6.5 milliseconds.